Welcome to Lecture 4, Old and New Problems of Induction. Here we'll take a digression through historical and foundational challenges posed for the prospects of a logic of induction. By the end of this lecture, you should be able to 1. Describe David Hume's old problem of induction. 2. Describe Nelson Goodman's new problem of induction. And 3. State why these two problems present challenges to the project of developing a satisfactory logic of induction. Recall that in previous lectures, we set up the challenge of an inductive logic as providing a rigorous, systematic account of each inductive strength and epistemic probabilities. That is, the evidential support provided by the premises of an inductive argument to its conclusions in the form of inductive strength or inductive degrees of support. And the kind of confidence or degrees of belief that we should then hold in the conclusion of such an argument, which we might call the epistemic probability that we should assign to that conclusion. We'll recap a few things. First, observing that while the domain of deductive logic is relatively well studied and its notions well defined, most importantly, the notion of validity, where a deductive argument is valid just in case it is impossible that the conclusion is false while the premises are true. Our corresponding definition for inductive strength, that is, our assessment of inference in the inductive case, is somewhat more imprecise, where we have an inductive argument is strong just in case it is improbable that the conclusion is false while the premises are true, and that this is not a deductively valid argument. Where the degree of inductive strength here depends on how improbable it is that the conclusion is false while the premises are true. But this notion of strength and this notion of degrees are not so neatly cashed out as the simple yes-no assessment of validity that we can find in the deductive context. And another fact to carry with us that we'll use during this lecture is that the factual claims made by the conclusion of a deductive argument are already implicit in the premises, and that this is a feature of all deductively valid arguments. To take an example of the following syllogism, Omid is a bachelor, all bachelors are unmarried, therefore Omid is unmarried, notice that the conclusion that Omid is married is already contained in the premises that Omid is a bachelor and in the definition of a bachelor as being unmarried. Nothing is pulled out, in a sense, by a deductive argument that wasn't already there in its premises. This is true of all deductive arguments, whether we are providing mathematical proofs. The truth of the conclusion was already contained in the axioms and definitions of the formal system with which we were working. This is true of relationships between ideas and all of the domains of application of deductive inference. And this is an important point to carry with us. In contrast, if an argument is inductively strong, its conclusion still makes a factual claim that goes beyond the information given in the premises. Consider the following example, where we have the inference from Nima has a fever, and people who have fevers often have infections, to Nima has an infection. This might be right, it might be relatively inductively strong, but notice that the fact that Nima has an infection is nowhere contained in Nima having a fever, or in people who have fevers often having infections, because it is indeed possible to have a fever and not have an infection. The fact isn't entailed by any of the definitions or posits of the premises of the argument. It really does go beyond those premises, and therefore involves the risk inherent in going beyond that factual information. One of the most important uses of inductive logic is informing our expectations of the future on the basis of the knowledge we have of the present and of the past, and more generally of the unknown on the basis of the known. Indeed, we can think of this as not just going beyond the past and the present to project into the future, but going beyond the portions of space that are familiar to us, say in scientific inference, to portions of space that are unfamiliar to us, or to instances with which we are acquainted, to instances with which we're not acquainted. The general pattern is going from things which we know to things which we do not. To this end, the two main challenges of inductive logic are first the construction of a system of scientific inductive logic, that is, a rigorous set of rules that guide us in making better inductive inferences, of doing a better job of extrapolating into the unknown based on the known, and the rational justification of the use of that system, as opposed to, say, any other system of inductive logic. To elaborate the latter point, we should give some account of what is it to provide a rational justification of an inductive logic. Here is one proposed definition that will be useful to us, and is something approximating what many past thinkers had in mind when grappling with the issue of how to provide such a justification for induction. Our proposed definition is that a system of inductive logic is rationally justified just in case the arguments to which it assigns higher inductive strength yield true conclusions from true premises more often than the arguments to which it assigns lower inductive strength. With this in hand, we can move on to the first of our problems of induction. This is a problem formulated famously by David Hume in his treatise of human nature. In short, when trying to justify induction, Hume observes that we have two methods of rational argument available to us: deductive argument and inductive argument. If we proceed by deductive argument for the efficacy of inductive inference, we find that it produces the wrong kind, fundamentally, of conclusion. And when we proceed by inductive argument, we find ourselves presupposing the very thing that we set out to demonstrate, the legitimacy of inductive inference itself. For the primary source for Hume's argument, I would point you to Book 1 of his treatise of human nature, in particular Part 3, Section 6, though he revisits this subject again repeatedly in his work. Hume observes that there are two types of rational arguments we could produce to justify the efficacy of inductive inference: an argument that is deductively valid, or an argument that is inductively strong. This observation of the two types of argument available to us in such a case is known as Hume's fork. What Hume shows is that neither sort of argument can do the job we would like it to. Let's look at why a deductive argument cannot do the work we want it to. So let us suppose that we try to rationally justify scientific inductive inference using a deductively valid argument. In a sound deductive argument, this is one that has not only that its inferences are valid, but that its premises are also true. We can use only premises we know to be true. Since we do not know the future, the premises that we use can pertain only to the present and to the past. But if the argument is indeed deductively valid, recall that deductively valid arguments can contain no claims in their conclusion that are not already present in their premises. Thus, the conclusion of such an argument can only refer to the past or present. But then justification of inductive logic requires an argument for why it will be successful in the future, not just in the present or the past. More generally, justification of inductive logic requires an argument for why it will be successful in unknown domains, not just in known domains. And hence, a deductive argument is simply not the right sort of argument. By its nature, does not have the resources to justify something like a scientific inductive logic. If you need a moment, feel free to pause and go back to revisit each step of this argument. Now we look at Hume's second fork and why an inductive logic will also not do the job. A common argument is that scientific induction is justified because it has been quite successful in the past. We might formalize such an argument as follows. Arguments that are judged by scientific induction to have high inductive probability have given us true conclusions from true premises most of the time in the past. Therefore, such arguments will give us true conclusions from true premises most of the time, past, present, and future. But observe that now we're engaged in circular reasoning. We're assuming that some form of scientific induction is in fact reliable to show that scientific induction is reliable. We're left then in an awkward position. It appears that deduction cannot do the job and induction cannot do the job. Hume's own solution was a peculiar one. He argued that inductive inference is a species of natural instinct, a habit or custom of the mind, which no reasoning or process of thought and understanding is able either to produce or to prevent. In short, that we cannot rationally justify inductive inference, but we will do it anyway, as a matter of psychological fact. Now, this may not be very satisfying, but we will see some marginally better responses in later lectures. Here I'd only pause to mention that Hume's response was found unsatisfactory by many scientists, philosophers, and thinkers throughout time, and many of those attempted to provide their own responses with limited success. In some form, Hume's problem endures to this day. Our second and new problem induction is from the philosopher Nelson Goodman, from his 1955 book Fact, Fiction, and Forecast. In short, Goodman observes that in trying to build a logic of induction, we face yet another challenge. When making inductive inferences, the logical structure of the descriptions of regularities do not tell us which regularities can be safely projected and which cannot. And by projected here, we mean taken from the domain of the known into the domain of the unknown, the essential task of inductive inference. For Goodman's original formulation of the problem, I can point you to his book, Fact, Fiction, and Forecast, and in particular to pages 59 to 83. But let's start with an example meant to motivate this problem of determining the projectability of natural regularities and the difficulties involved in this. Let's say that a certain thing, X, is said to be GRUE at a certain time t, just in case X is green at t and t is before the year 2100, or X is blue at t and t is during or after the year 2100. Right, so we should imagine that this thing is something that before our cutoff point, 2100, is green, and after that is blue. To this thing, we attribute the regularity GRUE, the property GRUE. And we can produce another such property, where we say a certain thing, X, is said to be BLEEN at a certain time t, just in case it is green at t, where t is before 2100, or it is blue at t, where t is during or after 2100. So these properties made of concatenating the initial and terminal segments of green and blue in the two possible orders are the ones we want to bear in mind. And to remember them, you can notice that each word has in it the color the thing will be before 2100 in its first half, and the portion of the color the thing will be after 2100 in its second half. Imagine a people speaking a language that had GRUE and BLEEN as basic color words, rather than the more familiar ones, green and blue, that we use. Now observe that taking a green bottle for such people and simply observing it before and after the year 2100 will involve it undergoing a change from GRUE to BLEEN, where prior to 2100 it was green, and therefore it was only GRUE and not BLEEN. But after 2100 it was green, and therefore it was BLEEN and not GRUE. For them, a change will have occurred at 2100. The insight here is that whether a certain situation involves a change or not may depend on the descriptive or linguistic machinery used to discuss that situation. Now, one might wish to object and protest that GRUE and BLEEN are not acceptable color words because, perhaps, they have reference to a specific date in their definition. One might think that that's the problem with these color words. But that property exists actually relative to our language. In contrast, speakers of the GRUE-BLEEN language can have GRUE and BLEEN as basic terms without any reference to time. And then they would have to define our blue and green as follows. For them, a certain thing X is said to be green at a time t, just in case it is GRUE at t, where t is before 2100, or it is BLEEN at t, where t is after 2100. And similarly, they would say a thing X is blue at a certain time, just in case it is BLEEN before 2100 and GRUE after 2100. Notice that for them, GRUE and BLEEN would make no reference to time, whereas green and blue would require reference to time. The point of this is to demonstrate that the logical structure of the definitions of regularities gives us no reason to believe that green and blue are not legitimate, even if they're unfamiliar color words. That is, their logical structure does not tell us that they would be bad for projection, and so lead to unreliable identification of when a change has occurred, or more importantly for us, unreliable inductive inferences. And let's see how this is so. To see why GRUE and BLEEN would lead to unreliable inductive inferences, let's consider two cases of inductive inference. First, with the familiar regularity of green. We have, for our argument, the premise that 100% of the time that emeralds have been observed, they have been green, followed by the conclusion that the next time that an emerald will be observed, it will also be green. Now we can do the same inductive inference, but with the property GRUE, where we have for our premise 100% of the time that emeralds have been observed, they have been GRUE, followed by the conclusion, the next time that an emerald will be observed, it will also be GRUE. Notice that these follow an identical pattern of inference. Notice also that if they're both done prior to the year 2100, they both will also have true premises. But by projecting the GRUE regularity, where it would be in effect predicting that emeralds will change colors after 2100, we're predicting that they'll become blue. Notice that this leads not just to a bad inference, but what we see is that two identical patterns of inference, both with true premises, lead to contradictory conclusions. Let's take stock of what we've learned so far. First, whether we find change or not in a certain situation may depend on the linguistic machinery we use to describe the situation. Relatedly, what sort of regularity we find in a sequence of occurrences may also depend on our linguistic machinery. Importantly, we might find multiple regularities in the same sequence of occurrences, the same facts, but where some of those regularities are successfully projectable and some are not, and that success is not obvious from their logical structure alone, such that the predictions arising from projecting them using the same pattern of inference may be contradictory. Now I'm going to work with you to drive this point home and draw out its implications by considering 3 examples. In the first case, you are given a challenge to observe the regularity. You are first presented with 3 boxes, in the first of which you find a green insect, in the second you find a yellow sponge, in the third a purple feather. And your task now is to predict what will be in the 4th box. You must look for regularity. And indeed, this might seem hard. But what I want to draw your attention to is that you can rig your inference. You can cheat in order to license an inference to, for example, a red mask. What this is meant to draw out is the way that you can produce regularities as a matter of logical fact that seem deeply questionable given what we know about successful prediction, at least intuitively. So how do we cheat in this case to license an inference to our red mask? Well, we can produce a regularity. Let's call this Merkle, and define a thing X as being Merkle just when X is an insect and X is green, or X is a sponge and X is yellow, or X is a feather and X is purple, or X is a mask and X is red. Now we've found the regularity. All the items in the boxes have been Merkles. If we project this regularity into the future, inferring that the next item to be observed will be a Merkle, we obtain the required prediction. We obtain the prediction, it will be a red mask. Because after all, we saw 3 Merkles before, we expect to see another Merkle again. But this is clearly an arbitrary inference, not the sort of thing we would expect to work reliably due to certain background facts we know about the way the world works and what sorts of things we can and can't expect reasonably in normal situations to appear in boxes and how they're related to one another. And yet, this sort of cheating to make our inference be anything we want it to be can always be done. That this sort of cheating can always be done, and that therefore any data is logically compatible with any prediction is a strong claim. So let me do some more work to animate it for you. Consider a small country that is conducting a census every 10 years. At the first census, at year 0, it observes 5 million for its population. At 10 years, it observes 7 million. At 20, 9 million. Now, given these data points, what should be our prediction for the population at 30 years? A natural prediction is provided by linear extrapolation. By drawing a line through the 3 points, we get the prediction that at 30 years the population will be 11 million. And yet this is not nearly the only curve or line compatible with our 3 data points. We could draw the following curve, which would predict 16 million. Or this curve, which would predict 6 million. And each are compatible with all of our data points. In fact, we can draw a curve that passes through the first 3 data points and produces any number whatsoever as its prediction for 30 years out. Further, there are infinitely many curves that can pass through any finite number of data points, and thus an infinite number of regularities present in the data. Similarly, consider the following sequence of numbers, 1 through 5. Given these 5 numbers, what should be the 6th element of the sequence? Well, if the generating function, that is, the function that produces this sequence, is given by the one that allows the kth number to be k, then the next element of the sequence is indeed 6. However, we also have the following generating function, given by taking the product of k minus 1 through k minus 5 and adding k. This produces the next element as 126. And again, for any finite string of numbers which belong to a series, there are infinitely many generating functions that produce that string of numbers and also produce whatever next number is desired. The problem we've observed is that whatever prediction we wish to make, we can find a regularity whose projection will license that prediction. Yet we know that not every prediction, and hence not every projection, is equally good. For example, that the population will grow from 9 to 10 to the 42nd million is likely not a great prediction. Neither is the projection that I used a generating function to make the preceding sequence of numbers that was 42 pages long. How might we construct then an inductive logic that identifies more and less projectable regularities? That seems like it will be essential to an inductive logic that will guide more and less accurate prediction. Goodman underscores this point as follows. To say that valid predictions are those based on past regularities, without being able to say which regularities, is thus quite pointless. Regularities are where you find them, and you can find them anywhere. In sum, we have learned from the old problem of induction that the justification of any scientific inductive logic cannot be done entirely deductively, and appears to require assuming an inductive logic itself, the circularity of which is discomforting. And from the new problem of induction that all methods of induction assume some regularities, but it is not clear from the logical structure alone which regularities should be projected and which should not. These are real and enduring puzzles. Yet we find ourselves caring a great deal about effective inductive inference for medicine, science, policy, indeed everywhere we need to make uncertain inferences about the world and to act on these inferences. So now we face the question of which methods of induction, whatever their limitations, are better or worse than other methods. we will see that there are in fact inductive logics that, while they do not resolve all the problems, have particular properties that may make them better than any other methods.